So, good afternoon and welcome back, students. Now, we will be taking up our next test, and that is F test. Okay. So, in our previous lecture, we have already mentioned that before applying t test, that is what we have studied in the previous lecture. For differences of two population means, one of the requirement is to check the equality of variances of two populations. Okay, that is, before applying the t-test, we have to test the equality of variances of two populations. Okay, and this assumption can be checked with the help of f-test. Okay, so what basic difference you other basic difference you can see between the chi-square test and this test is there only one sample is given. Okay, and you are comparing the things with a predefined or a hypothetical value, okay, of the variance. But in case of f test, now you are comparing the two population variances. Okay, and it is one of the prerequisite before you can go for the t test also. That is, before applying the t test, and if it is not given that there is equality of variances, then you have to conduct first the f test. And if you find that the two population are equal in variances, then only you can apply the t test. Okay, so this f test is also important in number of contexts. For example, an economist may want to test whether the variability in income differs in two populations. Okay. Similarly, a quality controller may want to test whether the quality of the product is changing over the time. Okay, whether it is getting better or it is getting worse, or whether it had remained the same over the period of time. So for that you have to apply the F test. Okay, and this test works under the following assumptions. What are those assumptions? That the populations from which the sample are drawn must be normally distributed. Second thing is, sample must be independent of each other. So earlier we were discussing about the one sample. Okay, here we will be discussing about the two samples. Okay, so let x1, x2, xn be the random sample of size n1 from a normal population with mean mu1 and variance sigma 1 square. Similarly, y1, y2, yn be the random sample of size n2 from another population with mean mu2 and variance sigma 2 square. And here we want to test the hypothesis about the two population variances. Instead of one, we are testing the hypothesis about the two population variances. Okay. So we want to test the hypothesis about two population variances. So we can take our alternative and null hypothesis as. So if it is a two-tailed test, then what we will be saying, that the sample variance of the one is equal to sample variance of the second, and its converse will be your alternate hypothesis. Similarly, in case of one-tailed test, it is that the first sample is less than or equal to the second sample, and its alternative will be its complement. And similarly, in the case of the other tail test. Okay. So for testing the null hypothesis, the test statistics f is given by f is equal to s1 square, okay, upon s2 square. That is the variance of sample 1 divided by the variance of sample 2 is nothing but your f statistics, which follow the f distribution at n1 minus 1 and n2 minus 1 degrees of freedom. Okay, so this ratio is going to follow the f distribution. Okay, and where this s1 can be calculated by using the formula 1 upon n1 minus 1 into sigma x minus x bar whole square, and this s2 will be, this will not be x actually, this will be your y. Okay, this will be your y, right? And here also, because we have taken this x1 and this is y. Okay, And here also in this formula, your this S2 can directly be calculated. For ease of calculation, you can calculate this x1, this S1 and S2 like this. Okay, so this S1 will be 1 upon n1 minus 1 into sigma x square minus sigma x, not sigma x square, this is sigma x whole square. Okay, this will be your sigma y whole square, not the y square. Okay, so this will be S1 square will be 1 upon n1 minus 1 sigma x square minus sigma x whole square upon n1, and this S2 square will be equal to 1 upon n2 minus 1 sigma y square minus sigma y whole square upon n2. Okay, so your test statistics F follows the F distribution with V1, that is N1 minus 1, and V2, that is N2 minus 1 degrees of freedom. Okay. So after substituting the values of S1 square and S2 square, we get the calculated value of F, which we call as F calculated. Okay, and we will compare this with our test statistics F, that is the table value. So we have to obtain the critical values or the cutoff values in the sampling distribution of the test statistics F, and then construct a region, critical region for the size, and the critical values of the test statistics F for various degree of freedom and different level of significance can be obtained from the table. So very elegant F table for various critical values can be downloaded directly from this site. Okay, if I click on this, so you will see, so these are the various this F values. So this is the degrees of freedom for the first variable, these that is the row wise, then these are the degrees of freedom for the second variable. Okay, and say for example first variable has 3 degrees of freedom, then we have to look in this, and second variable has 5 degree of freedom, then we have to look like this. Okay, and these are various level of significance, that is at 0.001, 0.01, 0.025, 0.05 and 0.100. Okay, so at different level of significance, that is alpha level. Okay, this has been given, right? So I will just do one more thing, I will just increase the size so you will be able to see. So what I was telling is that these in the rows, these are the first variable, in the column these are the second variable, these are the p values or the level of significances, and these are the f values. Okay, say for example if I have first variable is having 3 degrees of freedom, second having 5 degree of freedom, and if we want to see at 5% level of significance, so our f value will be 5.4. so this is how we see. So it is up to 9 here, then from 10 to 1000 it is here, and on the downside it is 8, 9, 10, 11, 12, 17. Okay, so like this it has been given up to 1000 downward. Okay, so this is how this table has been arranged. Okay, so for different level of significances at different degrees of freedom. Okay, and in this particular F table mentioned in this above, only the right-tailed critical values are given. Okay, if you see, so these F values are for the right-tailed test. These are not for the left-tailed. Okay, and if you want to conduct a test which is actually left-tailed, then for left-tailed you have to calculate the F value by your own. Okay, and how to do that? That is, there is a formula for that. Say for example, the left-handed tailed critical values of F test can always be obtained by the formula given below. That is, we have this left-tailed value V1 V2 1 minus alpha is equal to 1 upon F value for V2 V1 at alpha level of significance. Okay, so if we have this right-tailed value available with us, so making it its inverse will give you this one. Okay, left-tailed value, right? So this is how we can calculate. So when we will be doing some examples, so it will be more clearer. Okay. So now let us do one example for this F test. And The following data relates to the number of items produced in a shift by two workers A and B for some day. Say for example, there are two workers. One is A, one another is B, and they work on certain shifts. And then number of items produced by them are for A it is 26, whereas B has produced 19. A has 37, then B has 22, A has produced 40, B has 24, then A is 35, then B has 27, this 30, 24, 30, 18, 40, 20, 26, 19, like this. Okay, so assuming that the parent population are normal, can it be inferred that B is more consistent worker as compared to A? Okay, so here we want to calculate the consistency or the stability in the production. Okay, so here we want to test that worker B is more stable than worker A. As we know that stability of data is related to variance of the data, right? Okay, and smaller the value of variance implies data is more stable. If the variance is less in a data, then that data is more stable. If there is more variability, then that data is more unstable, right? Therefore, to compare the stability of two workers, it is enough to compare their variances, isn't it? If sigma 1 and sigma 2 denotes the variances of worker A and worker B, right, respectively, then what is our claim? We were telling that worker B is more consistent. It means the variance of first worker should be greater than variance of second worker. This makes our one statement. And what will be its converse? Its converse will be that variance of first worker is either less than or equal to variance of the second worker, because there is a equality sign. So this will be our null hypothesis. This will be our alternative hypothesis. Okay, so this is what I have shown here, that our null hypothesis will be sigma 1 square is less than or equal to sigma 2 square, and alternative is sigma 1 square is greater than sigma 2 square. That is worker B is more stable than worker A, right? Since the alternative hypothesis is right-tailed, isn't it? Because it is a greater sign. First sample is greater than second. So it is nothing but it is right-tailed, and all our values in table are also right-tailed, isn't it? So it is right-tailed, so test is right-tailed test. So here we want to test the hypothesis about two populations variance and sample size. N1 was 11, N2 was 9, okay, are small. Also the proportion under study are normal and both samples are independent. So we can go for F test for two population variances. So what will be our F test? So F test will be equal to S1 square upon S2 square, isn't it? So when we will be testing this as S1 square upon S2 square, so we have already these formulas, that is to I will just copy that one. S2 square will be this, this is this one. So your S2 square is 1 upon N2 minus 1 into sigma y minus y bar whole square. So what will be the calculations for S1 and S2, right? So we have this X available with us. I will do one thing to make it available in one page. This let it be 150, 35, right? Okay, so Basically these are the number of items produced by X, and what are their number? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, isn't it? Their total is 374. Okay, so if it is 374, then our this X bar can be calculated. So our X bar will be equal to X bar will be equal to 1 upon 11 into 374. Okay, so it will be equal to 34. Similarly, Y bar can be calculated. It will be equal to 1 upon 9 into 198 is equal to 22. So once we have these our mean values, so we can calculate the deviations. Okay, so this X minus X bar, that is 26 minus your 34 is minus 8, then 37 minus 36 34 is 3, then 40 minus 34 is 6. Like this we have found the deviation, it will always be equal to 0, and then there is square, so it came out to be 380. Similarly for Y, we find out this Y minus Y bar, and then Y minus Y bar whole square, so its values came out to be 380 and 80. So once we have this 380 and 80, then we can calculate this your S1 and S2. So your S2 will be like this. So 1 upon n1 minus 1 x minus x bar whole square. So this will be equal to 1 upon 10 into 380 is 38. So your S1 square is equal to 38, and your S2 square is equal to 10. Okay, so your F value, that is S1 square upon S2 square, will be equal to 38 upon 10 is equal to 3.8. Okay, and it came out to be at how many degrees of freedom? That is 11 and 9. That is V1 is 11 and V2 is 9. Okay, so when we will see in that table which I have shown, okay, sorry, these are not 11 and 9, these are 10 and 8, minus 1 we have to do. Okay, so when we will be seeing this in the table at 5% level of significance, its value came out to be 3.35. okay, so if I open this, okay, and see the first variable is 10, so I will go down and see at 10. Okay, and then I have to see at this at 8. Yes, so I am seeing at 5% level of significance, isn't it? So at 5% level of significance, 10 and 8. So on upper side it will be 10, 10, and on lower side it should be 8. So this will be this one, and it is the second value. So it will be 3.35. So it came out to be 3.35. Okay, so your this value is, here it is written 3.347 up to 3 digit. When we will round off, so it will become 3.35. So it is equal to 3.35. And what was our calculated value? Calculated value was 3.8. And we can see from the figure that it lies in the rejection region. So since the calculated value of test statistics, that is 3.8, is greater than the critical tabulated value 3.35, that means the calculated value of test statistics lies in the rejection region as shown in the figure given above. So we reject the null hypothesis and accept our alternative hypothesis. So our claim was correct at 5% level of significance. That is, this was rejected, and this is accepted. So we can say that the variance of the first worker is more than the variance of second worker. It means second worker is more consistent as compared to first worker at 5% level of significance. Thus, we conclude that the sample provides us sufficient evidence in favor of the claim. So, worker B is more stable or consistent worker compared to worker A. So, this is how we conduct the F test for these two population variances, right? Now, sometimes our I am having a call. Let me take that. Hello. ठीक है मैं क्लास खत्म होती था so now we will be taking up another angle of this thing, okay, so that you will understand from this example. So say for example in this particular example, this is example number 4 of this lecture. So here it is given that two random samples drawn from two normal population gave the following results. Okay. Say for example in first population size is 9 and their mean is 59 and sum of the square deviation from the mean is that is x minus x bar whole square. Okay. That is equal to 26 and second population size is 12, their mean is 60 and their sum of square of deviation from the mean is 39.6. Test whether two samples are from the same normal population. This is what they are asking. So what is the solution? Since we have to test whether both the samples are from same normal population, therefore we have to test two hypotheses separately. That is, first thing we have to test is that two population means are equal, whether the two population means are equal. If two population means are equal, then these are the same populations. Okay. Then we have to test that two population variances are equal. Okay. That is sigma 1 square is equal to sigma square 2. Okay. Now, since the sample size is small and the population under study are normal, so the two means will be tested using t-test. How you can test the means? Using the t-test, isn't it? Whereas two variances will be tested using the f-test, right? So, but t-test is based on the prior assumption that both population variances are same. Therefore, first we apply the f-test and later we will apply the t-test. Okay. So, when f-test accept the equality hypothesis. So, what has been given here? Here it is given that n1 is 9, your x bar is 59 and this is 26 and this value is 12, this is 60 and your y minus y bar whole square is 39.6. So we will calculate this S1 and S2 according to the formula. So once this S1 and S2 has been calculated, this S1 square is equal to 3.25 came out to be 3.25 and your S2 square came out to be 3.6. Okay. Now we will set up the null hypothesis. So what will be our null hypothesis? That sigma 1 square is equal to sigma 2 square. Whereas our alternative hypothesis will be sigma 1 square is not equal to sigma 2 square. That is H naught will be sigma 1 square is equal to sigma 2 square and our null hypothesis will be that sigma 1 square is not equal to sigma 2 square. Okay. So our f value when you will be calculating, so this f will be equal to s1 square upon s2 square is equal to 3.25 divided by 3.6 is equal to 0.8. Okay. Now we have to find the critical tabulated value of test statistics for two-tailed test. Now because there is a equality inequality sign in the alternative hypothesis, so it is a two-tailed test. We have to see the right tail also as well as the left tail also, right? So the critical tabulated value of test statistics for F2 tail test corresponding N1 minus 1, N2 minus 1, that is 8 and 11 degree of freedom at 5% level of significance is, so first one, that is 8 and 11 degree of freedom, it came out to be 3.66. Now for second one, okay, that is second, it will be 1 upon F 11 and 8 at, and here it will be alpha by 2, okay, because it is a two tail test, okay, so it will be at 0.025. So when you will see the F value at 11 and 8 at 0.025, make the inverse of it, that will give you the left tailed value, okay. So this is your right tailed value, this is your left tailed value. So your right tailed value, I will just make it little bit lesser, 120, so you can observe it, right. So in right tail test, your F value came out to be 3.66, and your left tailed, your F value came out to be 0.236, and your F value lies at 0.88. So because whether you take right tail or you take left tail, your F value resides in the acceptance region, isn't it? Because since the calculated value of test statistics equal to 0.88 is less than the critical value 3.66 and greater than the critical value 0.236. That means calculated value of test statistics F lies in the non-rejection region, and hence we support the claim. And what was our claim of null hypothesis? That the two population variances are same. So hence now equality of variance holds true, right? Thus, we conclude that both samples may be taken from normal population having equal value. Now, once we have tested that the two normal population are of equal, so our claim now we will be testing that mu1 is equal to mu2 and its complement is mu1 is not equal to mu2. That is, we will be conducting the t-test which we have done in our earlier lecture. So, this will be our null hypothesis and its complement will be our alternative. So this t-test will be calculated by using this statistic. That is, we will calculate the pooled standard deviation, and that by putting this pooled standard deviation, we will be calculating the value. Okay. So this pooled variance can be calculated using this formula. That is 1 upon n1 plus n2 minus 2, already discussed in previous lecture. So this xi minus x bar whole square plus yi minus y bar whole square. So putting all these values, you will be getting this as 3.45. So this standard deviation for pooled standard deviation will be square root of 3.45 is equal to 1.86. So your pooled standard deviation came out to be 1.86. Now your t statistics, when you will be putting these values, that is 59 minus 60 upon 1.86 into, when you will be calculating this 1 upon 9 plus 1 upon 12, so it came out to be 0.194. This all t calculated came out to be 1. Okay. So now this 1.22 at 19 degree of freedom at 5% level of significance for two tail test is plus minus 2.43. That is, at two tailed it will be 0.025, and this t value is less than the critical value 2.43 but is greater than this minus 2.43. That means the calculated value of test statistics lies in the non-rejection region. That is, if you see from minus 2.43 to plus 2.43, your minus 1.22 is in the acceptance region. Thus, we conclude that both samples may have been taken from the normal population having equal means. So hence overall, all because variance is same, mean is same, hence overall we can conclude that both samples may have come from the same normal population. Okay. So that completes our your F test, and what we have seen in today's lecture is that Then this chi-square and f-test are generally being used for comparing the variances. Chi-square is used when we have been already been given a hypothetical or a specified value, and in this we test the hypothetical variance, that is the sample variance, against a hypothetical variance. Okay, and it follows a chi-square distribution table, which I have already given. But when you will be having two samples, then we go for your f test. Okay, and this f test is used to check the equality of variance of two populations. Okay, and it can also be used for comparing the variability in two populations or in two samples. Okay, so when there are two and your variance is not known, that whether the two population variance is same or different, so for that you apply the f test. Okay, so this f test we have discussed, and it follows a f distribution. The only thing here is that for left tailed you have to calculate the value from the right tailed f values. Okay, once you have calculated, then you have to put the formula, set up the null hypothesis and the alternative hypothesis, and either accept or reject the claim. Okay, and accordingly you can draw and see that whether your calculated value lies in the acceptance region or the rejection region. If it is the rejection region, then your null hypothesis is rejected and your claim is accepted. Okay, so this is how we do, and then if they are asking for the normality of a population, then we, after doing the f statistics, then we can go for the t statistics, and after concluding that, then we can tell that the whether the two samples are from the same population or not. So that completes our this half test. And one of the student Viplav Sharma has said that share the notes, so that I will do. Okay, so I know that last 2 3 lecture notes are yet to be although those are completed already, so I will just share them on website. Okay, so it will be readily available to you for your revisions. Okay, so if no other question is there, uh, thank you very much for your patience hearing, and this is all from today's lecture. Thank you. Thank you very much.